Look at this map of our solar system and the nearest stars. From here to Alpha Centauri, our closest neighbor, the distance is about 4.37 light years. That is roughly 25 trillion miles. To put that in perspective, if you scaled the sun down to the size of a grapefruit, the next star over would be another grapefruit sitting somewhere in Antarctica. The sheer emptiness between them is almost impossible to grasp. So what does it actually take to cross that void? To send a spacecraft or a human being from one star to another? This isn't just about building a faster rocket. It is about rethinking the very foundations of propulsion, energy, and survival. The distances are so vast that our current chemical rockets would take tens of thousands of years to reach even the closest star. That is not a journey, that is a death sentence. But here is the thing we rarely stop to consider. The technologies needed to make this leap might already be taking shape in laboratories right now. The answer is not some science fiction fantasy. It is engineering we are beginning to build. So let's start with the obvious problem, the rocket equation. It is a brutal mathematical reality that governs every launch from Earth. To get a payload moving faster, you need more propellant. But that extra propellant adds mass, which means you need even more propellant to push that mass. It is a runaway cycle. For a chemical rocket to accelerate to interstellar speeds, the fuel tank would need to be larger than a planet. That is not an exaggeration. It is the tyranny of the rocket equation, and it is the reason we are stuck in the slow lane of space travel. Now here is the thing. Engineers have known about this problem for decades, and they have come up with some audacious ideas to break out of it. One of the earliest was nuclear thermal propulsion. The concept is simple in principle. You take a nuclear reactor, heat up hydrogen propellant to extreme temperatures, and then expel it through a nozzle. The exhaust velocity is far higher than anything a chemical reaction can produce. In the 1960s, NASA actually tested this under the NERVA program. They built and fired prototype engines on the ground. The results were promising. A nuclear thermal rocket could cut travel time to Mars by half. But for interstellar distances, even that is not enough. You would still need enormous amounts of propellant, and the journey would take centuries. So the next leap is nuclear pulse propulsion, and this is where things get truly bold. Imagine a spacecraft that carries a stack of small nuclear devices. You eject one behind the ship, it detonates, and the blast wave hits a massive pusher plate at the rear. The shock absorbs the energy and propels the ship forward. Then you repeat, over and over, each pulse accelerating the craft a little more. This was Project Orion, studied seriously in the late 1950s and early 1960s by some of the brightest minds at Los Alamos and General Atomics. The numbers were staggering. A properly designed Orion ship could reach speeds of up to 3% of the speed of light. That would bring Alpha Centauri within 140 years. Not a generation, a century and a half. Still long, but suddenly within the realm of possibility. Consider it. A single launch from Earth, a series of controlled blasts in the upper atmosphere, and then a steady acceleration across the solar system. The ship would carry its own fuel in the form of those nuclear pulses. The rocket equation is sidestepped because the propellant is ejected from the ship in discrete packages, not as a continuous stream. The mass ratio becomes far more manageable. But there is a catch. Project Orion was never built for interstellar flight. The test models were small, and the political and environmental concerns around nuclear testing in the atmosphere shut the program down in 1963. The idea lingered in theoretical papers, but it never got the funding to become real. And yet, the principle remains valid. If we wanted to send a probe to another star in our lifetimes, nuclear pulse propulsion is one of the few concepts that could actually get it there within a human timescale. The physics works. The engineering challenges are immense, but they are not fundamental showstoppers. The main obstacle is political will and public acceptance. So let us imagine that flyby mission to Alpha Centauri. A spacecraft weighing perhaps 100 tons. A stack of nuclear pulses, each carefully designed to maximize thrust while minimizing radiation damage to the ship. The acceleration would be gentle at first, maybe a fraction of a g. But over weeks and months, the velocity builds. By the time the ship leaves the solar system, it is moving at thousands of kilometers per second. It would take about 140 years to reach the target. The probe would send back data as it passed through the Alpha Centauri system, then continue into the void. That is not a dream. It is a design that has been sketched out on paper, modeled in computers, and debated in scientific journals. The technology is not science fiction. It is mid-20th century engineering that we never fully pursued. And that is the first piece of the puzzle. A propulsion system capable of reaching a significant fraction of light speed. Without it, interstellar travel remains a fantasy. With it, the door opens just a crack. But propulsion alone is not enough. You also need power. You need energy to run the ship's systems, to communicate across those vast distances, and to keep the crew alive if humans are on board. So next we have to ask where that energy comes from. And that leads us to the second great technological challenge. Propulsion gets the ship moving, but what powers the ship itself once it is out there? The answer is energy density. And when you start looking at the numbers, you realize that chemical batteries and solar panels are not going to cut it. Not even close. Think about it this way. A spacecraft traveling at 10% of the speed of light has an enormous amount of kinetic energy. To accelerate to that speed, you need to put that energy into the ship in the first place. And once you are cruising, you still need power for life support, navigation, communications, and scientific instruments. The sun's light grows dimmer and dimmer as you move outward. By the time you reach the Oort cloud, the sun is just another bright star. Solar panels become useless. So what do you use instead? But not the kind we use on Earth. Fission reactors have been used on spacecraft before, like the Russian Rorsat satellites and the American SNAP program. But those were small, low-power units designed for short missions. For interstellar travel, you need something far more potent. You need a reactor that can produce megawatts of power continuously for decades. And that is where fusion comes in. Fusion is the same process that powers the stars. It releases millions of times more energy per kilogram of fuel and chemical reactions. The most promising design for a spacecraft is the fusion drive, and the most famous concept is Project Daedalus. This was a study conducted by the British Interplanetary Society in the 1970s. They designed a two-stage probe that would use a pellet of deuterium and helium-3 ignited by electron beams. Each pellet would produce a tiny fusion explosion, and the resulting plasma would be directed out of a magnetic nozzle to produce thrust. The numbers are breathtaking. Daedalus could theoretically reach 12% of the speed of light. That means it could cross the 40 trillion kilometers to Barnard's star in about 50 years. Not centuries, decades. And the fuel mass required is surprisingly manageable. The first stage would consume about 50,000 tons of fuel pellets. That sounds enormous, but compare it to the fuel needed for a chemical rocket to do the same job. The chemical rocket would need fuel equivalent to the mass of a small moon. But here is the catch. We do not have the technology to build a Daedalus today. The fusion ignition systems are far beyond our current capabilities. The fuel, helium-3, is incredibly rare on Earth. We would have to mine it from the moon or the gas giants. And the engineering challenges of containing and directing a fusion explosion inside a spacecraft are immense. Still, the physics is sound. It's an engineering problem, not a fundamental impossibility. Now, let's take it a step further. Antimatter. If fusion is the fire of the stars, antimatter is something else entirely. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy. The energy density is off the charts. 1 gram of antimatter reacting with 1 gram of matter releases about 43 kilotons of TNT equivalent. That is more energy than the atomic bomb dropped on Hiroshima. And that is from just 2 grams of fuel. For a spacecraft, antimatter propulsion could theoretically reach 50% of the speed of light. The exhaust velocity would be close to the speed of light itself. The specific impulse, the measure of efficiency, would be orders of magnitude higher than anything else we have ever built. A mission to Alpha Centauri could take as little as 9 years ship time. That is within a human lifetime. A crewed mission becomes conceivable. But the challenges are staggering. Antimatter does not exist naturally in any useful quantity on Earth. We produce it in particle accelerators, but the amounts are microscopic. A single gram of antimatter would cost trillions of dollars to produce, and we have no way to store it safely. If it touches ordinary matter, it annihilates. You need magnetic traps, perfect vacuums, and fail-safes that can never ever fail. One containment breach, and the ship, and everything around it, is gone. Still, researchers are making progress. CERN has trapped anti-hydrogen atoms for several minutes. The technology is primitive, but it exists. The path from trapping a few atoms to storing a gram is long, but it is not blocked by any known law of physics. So here is where we stand. We have 3 viable propulsion concepts: nuclear pulse, fusion drive, and antimatter engine. Each one pushes the speed limit higher and the travel time lower. But each one also demands technologies we have not yet mastered. The question is not whether they are possible. The question is whether we are willing to invest the resources to build them. And that leads to the next piece of the puzzle. Even if we have the propulsion and the power, we still have to navigate through the interstellar medium. The space between stars is not empty. It is filled with dust, gas, and cosmic rays. At 10% of the speed of light, a grain of dust hits the ship with the force of a bullet. At 50%, it is like a nuclear explosion. So we need shielding, we need armor, and that is a whole new set of problems. These technologies aren't just theoretical, they are being researched in labs and universities right now. Engineers are working on the components, the materials, the power systems. They are laying the groundwork for missions that will not launch in our lifetimes, but will be built by our children. If you want to stay on top of this engineering frontier, make sure you are subscribed to Future Frontiers. We are tracking every breakthrough, every setback, and every audacious idea that brings us closer to the stars. Hit that subscribe button and join us for the journey ahead. Now let's zoom out across the entire length of a hypothetical interstellar journey. Because even with the perfect propulsion system and the ultimate power source, you still have to keep the crew alive for decades or centuries, and that changes everything. Think about what a human being needs to survive: air, water, food, warmth, gravity, protection from radiation, and psychological stability. Multiply that by a crew of 10 or 20, and you are looking at a life support system that must operate flawlessly for generations. One failure, one sealed door that leaks, one pump that stops working, and everyone dies. This is the reality of a generation ship. A vessel so large and self-contained that it becomes a world unto itself. The crew that launches from Earth is not the crew that arrives. Their children, and their children's children, will be the ones to see the new star. The original crew will have passed, their bones carried along in the cold metal hull, never knowing if their sacrifice was worth it. It is a profound ethical and engineering challenge. How do you design a society that remains stable for hundreds of years? How do you prevent the knowledge of the mission from being lost? How do you maintain the technology, the propulsion, the navigation, when the people maintaining it were born in space and have never seen a planet? And then there is the biological problem. Human reproduction in microgravity is poorly understood. The effects of cosmic radiation on fetal development are even less known. A generation ship is not just a spacecraft, it is a floating civilization, and we have no idea how to build one that works. But there is another path. The sleeper ship. Instead of raising generations in transit, you put the crew into suspended animation, hibernation, cryogenic sleep. The idea is that the human body is cooled to just above freezing, metabolism slowed to a crawl, and the crew remains unconscious for the entire journey. They wake up at the destination, having aged only a few years, while decades or centuries passed outside. The concept is seductive. It solves the social problems of the generation ship. There is no crew turnover, no cultural drift, no risk of rebellion. The same people who leave Earth are the ones who arrive. But the biology is brutal. We have never successfully revived a human from deep hibernation. The damage from ice crystal formation, from cellular degradation, from the sheer time spent in stasis, is immense. There are theoretical approaches, like using perfluorocarbon fluids, that replace blood and prevent ice formation. But they have only been tested on small animals. The leap to humans is enormous. And even if you solve the hibernation problem, you still have to wake them up. That requires a reliable automated system that functions after decades of inactivity. One computer failure, one power glitch, and the crew sleeps forever. So the engineering challenge is not just propulsion, it is survival, and this is where a radically different approach comes in. The Breakthrough Starshot project. Instead of sending humans, you send a swarm of tiny probes. Each one is a wafer of electronics, a few grams in weight, attached to a light sail. A massive laser array on Earth fires at the sail, accelerating it to 20% of the speed of light in minutes. The probes reach Alpha Centauri in about 20 years. No crew, no life support, no hibernation, no generation ship, just data. The probes fly through the system, taking pictures and measurements, and beam the information back to Earth. The journey is one way. The probes are expendable. The entire mission is a flyby, not a landing. But the data would be revolutionary. Here is the thing. Starshot is not science fiction. The laser technology exists. The sail materials are being developed. The miniaturization of electronics is proceeding faster than anyone predicted. The main obstacle is the laser array itself, which would need to be built in a high desert location, probably in the Atacama or the Himalayas, and would require gigawatts of power. But it is feasible. The cost is estimated in the billions, not trillions. So we have two fundamentally different visions of interstellar travel. One is the ship with a crew, facing the biological and social challenges of a multi-generational journey. The other is the swarm of tiny probes, sacrificing human presence for speed and simplicity. Both are being worked on. Both have passionate advocates, and both will require breakthroughs in materials science, power generation, and autonomous systems that we do not yet have. But the key insight is this: we are not waiting for some magical new physics. The technologies we need are extensions of what we already know. Fusion, laser propulsion, advanced materials, artificial intelligence, closed-loop life support. Each one is being pursued for its own reasons, for terrestrial energy, for computing, for space exploration. The pieces are being developed independently. The challenge is to assemble them into a coherent mission. And that is where the next section comes in. Because even if we solve propulsion and survival, we still have to figure out how to navigate across the void. The interstellar medium is not empty. It is filled with hazards that can destroy a ship in an instant. And that brings us to the third and perhaps most overlooked challenge of all. And that brings us to the energy and materials side of the equation. Because even the most elegant propulsion concept is useless if you cannot generate enough power to run it, or build a structure that survives the journey. Think about the numbers. A nuclear pulse ship, accelerating to 3% of the speed of light, has kinetic energy equal to about 10,000 times the total energy released by all nuclear tests in history. That is the energy you have to put into the ship. And once you are moving, you still need power for every system on board. The sun is a dim dot behind you. Solar panels are worthless. So where does that power come from? Imagine a massive laser array on Earth, or an orbit around the moon, firing a concentrated beam of light at a spacecraft. The ship carries a sail that reflects that light, converting the momentum of the photons into thrust. No onboard fuel needed, no propellant mass, just pure energy pushing you forward. This is the core idea behind Breakthrough Starshot, a ground-based laser array with a power output of about 100 gigawatts. That is roughly the output of 100 nuclear power plants, all focused into a single beam. The beam hits a sail just a few meters across, made of a material so thin and reflective that it is measured in atoms. The sail accelerates at tens of thousands of Gs. The probes reach 20% of the speed of light in under 10 minutes. That laser array does not exist yet. The engineering challenges are staggering. You need thousands of individual laser modules, each one precisely phased so that they all act as a single coherent beam. The beam must stay locked onto a sail the size of a dinner plate from a distance of millions of kilometers. Any misalignment, and the energy misses entirely, or worse, burns through the sail. And the sail itself is a problem. It has to be incredibly thin to be light enough to accelerate that fast, but strong enough to survive the intense heat and pressure of the laser beam. The leading candidate is molybdenum disulfide, or a layered structure of graphene and silicon dioxide. A sail that is only a few hundred atoms thick, but can withstand temperatures of several thousand degrees, is not something we can manufacture at scale today. But the research is moving fast. Beyond the sail, you also need the probe itself, a tiny wafer of electronics weighing just a few grams, containing cameras, sensors, a power source, and a laser communication system. The power source is a small radioisotope thermoelectric generator, basically a speck of plutonium that decays and produces heat, which is converted to electricity. That is enough to run the probe systems for the 20-year journey and for the few minutes it takes to fly through the Alpha Centauri system. Then there is the communication problem. The probe has to send data back from 4 light-years away. The signal is incredibly weak. The solution is to use the same laser array that launched the probe, but in reverse. The array acts as a giant telescope, collecting the faint photons from the probe's laser and amplifying them. It is a closed loop. The same infrastructure does double duty. So the pieces are coming together. The laser technology, the sail materials, the miniaturized electronics, the communication system. Each component is being worked on in labs around the world. The goal is to have a working prototype within a decade and a full-scale launch within a generation. But here is the deeper point. Starshot is not just about sending a tiny probe to another star. It is a proof of concept. If we can build a laser array that accelerates a gram-scale probe to 20% of the speed of light, we can scale that up. Larger sails, more powerful lasers, bigger payloads. The same technology that sends a wafer to Alpha Centauri that sent a kilogram-scale probe to Barnard Star, or a 100-kilogram probe to the Oort cloud. It is a stepping stone, and that is the pattern across all these technologies. Nuclear pulse propulsion, fusion drives, antimatter engines, beamed energy. They are not competing visions, they are stages in a progression. Each one solves a different piece of the puzzle. Nuclear pulse gets us to a few percent of light speed. Fusion pushes that to 10 or 20%. Antimatter could push it to 50% or more. Beamed energy gives us a path to launch without carrying fuel. The materials we need are also evolving. Carbon nanotubes for ultra-strong tethers and sails. Graphene for lightweight heat-resistant structures. Aerogels for insulation and impact shielding. These are not science fiction materials. They are being produced in laboratories today. The challenge is scaling up production to industrial levels and testing them in the conditions of deep space. So the question is not whether we have the technology, it is whether we have the will to develop it. The cost of a full-scale Starshot laser array is estimated at $10 billion. That is about the same as the James Webb Space Telescope. A fusion-powered probe like Daedalus would cost far more, but it would also open up the entire galaxy. The return on investment, in terms of scientific knowledge and human inspiration, is incalculable. And this is where we stand right now. The first interstellar probe could launch within a human lifetime. Not a century from now. Within the next 50 years. If we choose to make it happen. The technologies are being developed. The physics is understood. The only missing ingredient is the decision to build. So as we move into the final section, we have to ask the hardest question of all. not about propulsion or power or materials, but about us. Are we ready to become an interstellar species? And what does that mean for who we are? So that is the real question. Not whether the physics works, it does. The engineering is hard but not impossible. The real question is whether we have the patience to commit to a project that will not pay off in our lifetimes. The first probe to Alpha Centauri will take decades. The people who design it will be gone by the time the data returns. The children watching the launch will be the ones seeing the first images of another star system. That demands a kind of faith in the future we rarely practice. But we have done this before. The Voyager spacecraft, launched in 1977, still sends data back from interstellar space. Its designers are now in their 80s and 90s. We just have to do it again, on a grander scale. If you want to stay on this frontier, subscribe to Future Frontiers. We track every breakthrough and audacious idea that brings us closer to the stars.